Okay, the recording is now on. So like I just said a second ago, if I ever forget to turn on the recording, please remind me. And also, I noticed when I was looking at the recording of our last class session, for some strange reason, the little video box with me, uh, it disappeared partway through the class. And it wasn't, I didn't turn it off. I don't know what happened to make it go away. Now, during that time, I did show a few things. Um, I did make a few movements and things with my hands that you guys missed because you didn't see the camera. But the words that I used, I think, were adequate. That I don't think anybody had any problems. But if anybody sees the video link disappear, please let me know. Okay. So you never know. Next time around, the lack of video might be a problem. Okay. So I guess let's go ahead and get started. First thing, of course, will be questions about the homework. So unless anybody has any general questions, I'll go ahead and just jump right into the homework questions. I don't see anybody asking questions, so okay. So here are the answers to the homework problems that you haven't already looked up. As usual, I'm trusting that if you had I'm trusting that you've already looked up the answers to the odd number ones. So I'm just putting the even number ones. Or if there are any odd number ones where they didn't have the answer in the book, I put those. Okay. So I'll give you a minute or two to look at those.
Could we go over question 11?
Okay, question 11. What's your question?
I think I was just a little bit confused by what it was asking or what it meant. Maybe you could explain it.
Okay. All right. Well, if you look at the answer here, that's my way of remembering what the question is. So so the question must have been, how do you, in fact, well, yeah, I'm sure. The question was, how do you go about measuring the electric field, right? That was the question.
In
Okay.
space.
Say that again?
How do you go about measuring the electric field in space?
Well, or just anywhere. Okay. All right. So the answer is, you take a small positively charged object, and we're going to call that the test charge. And it's important that it has to be small and it has to be positive, and it has to be weakly charged, because if it had a strong charge of its own, the fact that it has a charge on it, its electric field would mess up the electric field of the space that it's around. So if it has a really small magnet or a small electric field compared to the field that it's in, then its effect on the field around it will be negligible. So you want it to be small and weakly charged, and it has to be positively charged. That's important because we've defined things in terms of positive charges. So when you take this small test charge and you place it somewhere, it's going to feel some force acting on it. And so then what you do is you say, okay, whatever direction the force is, that by definition is the direction of the field. And that would only be the case if it's a positive test charge. If it's a negative test charge, it's going to be different. And so to find out the magnitude of the electric field, you just take whatever the magnitude of the force is divided by however much charge is on your test charge. Or an easier way to do it is just take a test charge that has exactly 1 coulomb of charge. That way, when you divide by the charge, you're dividing by 1. Okay. So in that case, the magnitude of the force vector will be the same as the magnitude of the electric vector. But in general, that's how you do it. Okay, so I see that somebody's asking about question number 8 and number 10 as well. But before we go on to those, can you give me some feedback? Did I adequately answer your question there, Maddie? And anybody else who had a question on number 11? Okay, I'm not seeing any yeses or nos. So I need to know yay or nay.
I'm sorry, could you repeat the question?
Yeah, I think it helped me.
Okay, all right. So Jaron, what do you want repeated?
Okay, could you repeat the question? Because what was it that you asked that it has to do with question 11 and determining electric field?
Yeah, okay, so the question in 11 is, how do you determine what the electric field is at some point? Now, the fact that they said in space, don't let that throw you off. I don't care whether it's on the Earth or in space or wherever, just any point anywhere. I want to know what the electric field is. How do I go about doing it? And then what I just explained verbally and what you see on the screen right here, okay, that is the answer to that question. Okay, so I'm seeing that people are saying yes, that adequately answered the questions. Okay, so how about number 8 here? So let's see, what is question 8 asking? Okay, so apparently with question number 8, let me get my book here. Apparently they were just asking us to calculate the field. But let me open up my book here.
Yeah, I did the math on number 8 again, and 7.2 times 10 to the negative 6 over 1.6 squared, and I ended up getting 2.8 to the power times 10 to the 4th power, not 2.6 times 10 to the 4th power.
Okay, so you're thinking that maybe I got a weak point here. That has certainly happened before, and it could happen again. So hang on a sec. Let me get my glasses. Make sure I didn't make a mistake. Okay, so we want to know the electric field at a position that's 1.6 meters east of a
I might have
charge.
forgotten to multiply by K.
Oh, yeah, if you forgot to multiply by K, then that'll explain it for sure. That would be why you got a different answer than I got. Okay, so tell you what, let me just do it real quick here. Whoops, why did it go there? Okay, so let me just open up a text box here. Why is it behaving differently than usual? I'll tell you what, let's forget the text box. Let me just get at my calculator. Okay, so the electric field at position such and such. Okay, so the electric field is equal to the charge that they're interested in, which is 7.2 times 10 to the negative 6 times K, which is 9 times 10 to the 9th. And you have to divide that by the distance squared, which is 1.6. Don't forget to square the distance. So I get...
yeah, I forgot to multiply by K.
Yeah, so I'm getting the same answer here. I'm getting 2.6 times 10 to the 4th.
Yeah, I got the same answer when I multiplied by K.
Okay. Yeah, don't forget the K there. That K is very important. All right. So, all right. So now the question from Ellie is, how was the direction determined? Well, so it says here that it is a positive test charge, right? Okay. So by definition, the electric field is always the direction that if you were to take a positive test charge and you place a positive test charge 1.6 meters away from the charge that they gave you. So if that charge is positive and the test charge is positive, they're going to repel, right? That's how you get the direction. Remember that whenever you're doing this, the test charge is always, always positive. So hopefully that answers your question there, Ellie. And any other questions anybody has? I saw somebody was asking about question 10 a while back. Do you still want to do question 10 or are you okay with that? Okay, so Ellie is saying yes, that answered her question. I forget who it was that was asking about question number 10. But if you want to ask your question, go ahead. Otherwise, if I don't see anything appear in the chat box here, I'm going to assume that you're good. Okay, for number 4, you got 10 to the negative 8. And Andre does want number 10. So, okay, so, all right, so tell you what, let's do number 10 first, because that's the one I was asking about. All right, so number 10 says, how far away must a test charge be placed to measure a field of whatever? Okay, so let's see if there's a good way that I can do this. Let me open up a test box. Oops. Why does this not want to work? Okay, I got too many things on my screen here. Okay, how about I just talk you through it? Okay. So we want to know the distance, we know the field, okay? So if the equation, okay, I got an idea here. Okay. How about if we do this? Okay, can you all see me really big now? All right. So the equation says the electric field is defined as the oops. That again. So the electric field is defined as K times the charge divided by the distance squared. Okay, everybody all seeing that? Okay, so we know the field, we know K, we know the charge, we want to know what the distance is. So all we have to do then is just solve that. So let's swap places with those guys. So that R squared equals KQ, that's a K, over the electric field, take the square root of both sides, and bingo, you get the answer. So I hope that answers your question there. Okay, so let me turn the my sharing of the screen back on again. Okay, so now you don't have my big face jumping out at you like we did. Okay, what happened to our chats? Where did they go? Let me get the chats back up here. Okay, so looks like there was a question about number 15, but okay, so let me go back here because Joey had a question about number 4. So on number 4, you got 10 to the negative 8. I guess we could do it. Did anybody else get 10 to the negative 8, or the rest of you guys getting what I got? Okay, so Ellie's got what I got. So Joey, I'd recommend just go back. Maybe you punched the number into your calculator wrong. Okay, so let's go on. So there was a question about number 15. Was that it? I don't remember asking about 15. Did you mean 14? Okay, so Jaren's saying you still need, yeah, Jaren's saying you need help on number 4. Which one is number 4? Okay, number 4. Okay, so you've got a pith ball that weighs a certain amount and it's in a downward electric field. Okay, so let me draw it here. This is way easier than trying to draw it on the field here. Okay, so a pith ball is just a very light ball, you know, like a little fuzzy foam ball that doesn't have enough mass to worry about. And it's in an electric field. And it says that the electric field is a downward electric field. Okay, so that means you've got the electric field is looking like that. And let's assume that it's a uniform electric field. They didn't specifically say it's uniform, but I'm gonna assume that it is. And we're gonna talk later about how important it is to have a uniform electric field. Okay, so we've got a little ball that's placed in the electric field here. And let me get my glasses. Okay. So it has a charge of, oh no, we're supposed to figure out what the charge is. So we know what the weight is. Okay, so this pith ball has weight on it. Okay, so there's mg for the ball. So gravity's pulling it down, but it's not going down. It's being held up because there's an electric force. There's an upward electrical force that's exactly equal and opposite to the downward gravitational force. So we've got mg going down and we've got the electric force going up. Okay, so the force electric, which is of course K times Q1 Q2 over R squared. Or another way to remember it, what's the definition of the E field? Remember, the E field is defined as the force divided by the charge. Okay, so what that means then is that the force must be equal to the E field times the amount of charge. So we could use this definition over here if they give us the right information. But in this case, they didn't give us that information, but they did tell us the E field. So let's go with this one over here. Both of these are equivalent ways of defining the force. Okay, so they're telling us that the E field is 6.5 times 10 to the 4th. So we know that that's 6.5 times 10 to the 4th. Okay, So we know that this upward force and that downward force must be equal. So that means that E times Q must equal M times G. And so they tell us M, they don't tell us G, but we know G, and they tell us E. So Q then must be equal to mg divided by E, and voila, we're good. Okay, I'm hoping that answered your questions. Let me see if anybody else have any other questions? Okay, so I'm seeing a couple people saying that they did number 4 again, and they got 10 to the negative 8. Okay, a bunch of them, so maybe I got it wrong. Hang on just a sec while I take care of one thing. I'll be right back.
Your microphone's muted.
Thank you. Okay, so it's possible I did it wrong. Let me do it real quick here. Okay, so, oh boy, I hate wearing glasses. Okay, so they tell us, oh, okay, now notice when they give us the pith ball, they don't tell us how many kilograms it is. They tell us what it weighs. So this mg here, we don't want to multiply it by g because they've already done that. So they're saying the pith ball weighs 2.1 times 10 to the negative 3. Okay, and they're telling us that the E field is 6.5 times 10 to the 4. That's a positive 4. So let me see what I get when I put in my calculator. So 2.1 times 10, oops, times 10 to the negative 3, right? Divided by 6.5 times 10 to the 11th, right? Oh, 10 to the 4th, that's a 4. Okay. All right, so 2.1, 10 to the negative 3, 6.5, 10 to the negative 4. Okay, I get 10 to the negative 8 too. Oh my goodness. Okay, maybe I just typed it wrong. Okay, that's a wig point. Thank you for catching that. Let me go in and fix that. Maybe I just typed it wrong when I did it. Okay, so yes, definitely a wig point. Okay, any others? So I'll give you a second to type. If nobody has any questions, I'll move on, but I'll give you a few seconds here to type yay or nay about questions. I'm not seeing any. Okay. All right, let's go on to the new material then. Okay. So we hopefully now understand about electric fields. And so now today we're going to find out why electric fields are useful, at least one of the reasons. There's a whole lot of reasons. Okay, so when you look in the book here, and I know you always read the book before you do the homework, right? So you're going to see they talk about something right here called electric potential. Now, the word potential is, I think it's kind of an unfortunate choice of words on their part, because when you see the word potential, you think about potential energy, right? So like if you think about gravitational potential energy, if you've got a ball here, and so gravity is pulling it down, so you reach in with your hand, you push the ball upward, right? So you do some work on the ball. And in order to push the ball upward, you have to push with a force that's equal to mg. And then the distance that you push the ball is h, that's the height, okay? And so you have increased the energy of the ball. So the ball now has gravitational potential energy that it didn't used to have. All right, so when you hear the word potential energy, you think of that. Well, electricity works the same way. If you have a ball down here, You can all see the cursor. Okay, good. If you have a ball down here that's negative and a ball here that's positive, they want to attract each other. And so you could do the same thing here. You could put your hand underneath the ball. You could push the ball upward. And so you've given the ball energy, but it's not gravitational potential energy. This time it's electric potential energy. And so when they use the word electric potential, they're talking about that kind of thing, except the word electric potential and electric potential energy, they are not the same. To tell you what, I will come back to these things here. I want to approach these in a little bit different order than, okay, this is the order I want to talk about. Okay, so electric potential and electric potential energy. Be careful. There are two terms there that do not mean the same thing. Okay, so when they talk about the electric potential energy, then that is kind of like the gravitational potential energy that you're used to. But when they talk about just electric potential without the word energy at the end, if they just say electric potential without saying electrical potential energy, they are not talking about electrical potential energy. They're not talking about the amount of work you're doing. The electric potential is not measured in joules. Electric potential is something different. So let's go back now. And okay, so let me go back to where we started from. Okay. So this is what they are defining electric potential to be. And right up here, instead of having an equal sign, what we really should have is we should have three horizontal lines, because what you see here, this is the definition of electric potential. So the definition is however much work you do when you move a charge from one position to another charge, divided by the amount of charge that was on the thing that you moved. And the units for it are volts. Now, here is, volts is a word that I know you guys have heard all your life. You've worked with batteries, and you know that different batteries have different voltages. These guys over here, you know, this is a AA battery, this is a AAA battery, and many of you probably know that the voltage on them is 1.5 volts. Now, up until now, you may not have known what a volt is, but you do know that it's a measure of how much oomph a battery has. And so like this battery over here, this squarish one, I'm willing to bet that you guys could recognize right off the bat how many volts that has. Can somebody type in the answer? How many volts does that rectangular battery have there? 9. Okay, very good, yes. Okay, so what that means is that this battery here has a lot more oomph than these batteries over here do, because it has 9 volts and they only have 1.5 volts, okay? Now, there's a reason why I say how much oomph it has, because some people say, well, that means it has more power. No, power is different. And some people say, well, that means it has more energy. No, energy is different, okay? Voltage is what you see here. It's basically this, okay? Here's the way that I recommend you think about it. If you were to take this battery and you were to connect a wire directly from one end to the other end, which is not a good idea, okay? What would happen is that the electricity would just flow right through there. And there's really nothing stopping it. So all your electricity is going to drain very, very, very quickly. And the battery is going to get really hot. And the wire is going to get really hot. And in fact, it could melt. If we were in my classroom right now, I would go over to the wall, which I sometimes call the wall of shame. And I have some wires there that are melted because somebody did exactly this. They just hooked up a wire directly from the positive side to the negative side, and so much electricity flowed through there that it got so hot it actually melted the wire. Okay, so you don't want to do that. You need something there that either resists the flow or stops the flow completely. So what I've illustrated here is, imagine I have a magic hand where I can stick my hand in the wire and I can stop the charges from flowing. So on the one side over here, I have the charges are all squished together really tightly, and so there's a force. They remember, plus like charges repel, right? So on this terminal of the battery right here, there's a whole bunch of like charges that are all trying to get away from each other. And so I like to think of it in terms of electrical pressure. I like to say that there's a high pressure of positive charges here. They're all trying to get away from each other. Now, if I put my hand there to stop it so they can't get away from each other, but then not just, I don't want to just hold my hand still. I'm going to move my hand. And in fact, what I'm going to do is I'm going to put my hand so it starts at one side of the battery, and I'm going to push those charges all the way from one side of the battery to the other side of the battery. Now, they're pushing back, so it means I have to exert a force, and I'm exerting that force over a certain distance. So force times distance is work. So when I push these charges through there, I am doing work, all right? And so the way they've defined things is if I do 1 coulomb of work and the amount of charge that I've pushed from one side of the battery to the other, I'm sorry, let's go back and start that again. If I push 1 coulomb of charge from one side of the battery to the other, and the amount of work that I have to do is equal to 1 joule, then by definition, that battery has 1 volt on it, okay? So that's the way it works. So the voltage is defined as the amount of work that I do divided by the charge. So in this particular case, we know this is a 9-volt battery. So that means that if I were to push 1 coulomb's worth of charges from one side of the battery to the other, I would have to do 9 joules of work. Now, what if I push 2 coulombs? So I've got the same battery, it's a 9-volt battery, but this time the amount of charge that I'm pushing is not 1 coulomb anymore, it's 2 coulombs now. So that means I'm going to have to do 18 joules of work, okay? So, right, so over here, so this is the key thing here, the electric potential difference, not the electric potential energy, okay? The electric potential difference is the amount of work that I have to do divided by the amount of charge that I push, okay? Now, when you take my electronics class or my robotics class, I like to think of it in terms of the pressure. I tell people to think of voltage as the equivalent of electrical pressure. The more tightly you squeeze the charges together, the harder it's going to be to push them from one side to the other, okay? So basically that's it. That's what voltage is. And so that's going to be an important part of tonight's homework. So I don't see any questions, therefore I'm going to go ahead and move on. Okay. All right, so remember electric field lines, they're important. So this is just a review of what we talked about last time. So if I have a positively charged object, and if it's a point object or if it's a spherical object, if I were to take a positively charged test charge and put it here, the force is always going to be pushing away from it. Okay, and so the electric field lines are going to look like this if it's a positive charge. Now, if it's a negative charge, okay, if I take a positive charge and I put it right here, it's going to feel a force going that way. And so the electric field lines that are around a negatively charged object, they go like this. Okay, keep this in mind because this is going to become really important in our homework. Okay, so if you're around a point charge, this is what the fields look like. If, however, you've got multiple charges, the electric fields can get really weird. You can get some really, really strange shapes here. So in your homework, we're not going to give you any weird shapes like this. We're going to keep it simple. It's either going to be a point charge, so you have nice field lines radiating outward in a nice direction that looks like this. Or the other thing that we're going to do to you in the homework, and in fact, this is the thing we're going to do to you more often than not, we're going to set up a thing here that's called a parallel plate capacitor. So imagine this. Imagine I've got a piece of something, a piece of metal or whatever, and I've got another piece of something, okay? And I'm going to put them like this. So I'm going to put one directly above the other. And I'm going to put a positive charge on one of them and a negative charge on the other. Okay, So I got a positive charge on one, a negative charge on the other, right? This is called a parallel plate capacitor, and it turns out to be tremendously useful in physics because it has a really neat property. If you look at the electric field lines in this region, in between the capacitor plates, you'll see that the electric field is uniform. So that means we have a constant field. If I start right here at the top plate and I move downward here, the field strength is constant the entire way. And if I go outside the plate, then weird things happen. Now you can see that the lines are going all sorts of things. So if I were to go like from here to here, the electric field strength is changing. And so that means that the force that's acting on my object is going to be changing. And so if I want to calculate the work that I'm doing, I'm going to have to use calculus. Oh no, it's calculus, okay, because the force is changing. The one named Satchel, okay, I'm not quite sure what you meant there. Okay, so in your homework, they're gonna say, okay, we have a charge that's located somewhere, and we push that charge to some other place. How much work do we do on it? So if we are anywhere outside of our our parallel plate capacitor, the force is changing, and so calculating the work would be very, very difficult, unless of course you know calculus. And some of you do, but we're going to assume here that you don't. So everything in your tonight's homework can be done without calculus. That means that any homework that we do tonight can only be done inside the parallel plate, because that's the only place where the field strength is constant. Okay, so let's move on from here. Okay, so with that understanding, okay, it turns out that there's another way to think about electric potential difference or voltage. It turns out that the voltage is equal to the strength of the electric field multiplied by the distance that you push the object, but only if it's in a uniform field. In fact, let's see. So here, this is the one we already talked about. So let me skip over here. Okay, so this is only going to be true if it's in a uniform field. All right, so I'm sure you guys can see what's coming here. So what you see at the top of the page, that is not the definition of voltage. That is a very useful relationship. It's a true statement, but it's something that is derived from the definition. Okay, so we are going to go through and we are going to derive that right now. So we're going to start with the definition of voltage as work over charge. So I'm sure that you guys have all got your notebooks out. So you know the standard way we do things here. This derivation that we're about to do might very well be a question on our next test, wink, wink, nudge, nudge. So I definitely recommend you take notes on this derivation. Okay, so what we're going to do is we're going to start with the definition of voltage. So this is a good starting place. This is a definition. And when you're doing derivations, it's okay to start with definitions. Okay, so we start with the definition of voltage, which is work divided by charge. Okay, and we know that work is equal to force times distance, right? Okay, so we make that change. Okay, and then we say, okay, well, I can take force times distance over charge, and I can rewrite that as force over charge times distance. That's just algebra. Anybody can do algebra, right? And so then next thing is I say, okay, well, force over charge, that looks awful familiar. That's the electric field. That force over charge is the definition of electric field. So now what we have is we have the delta V, which is the electric potential difference, is equal to the electric field times the distance, which is exactly what they claimed up here it was. Okay, so this is going to come in very, very handy, that the change in voltage is equal to the electric field times the distance that the object moves. But do not forget, this is only true if you are in what we call a uniform field, because if you're not in a uniform field, the force will not be constant. Work is only equal to force times distance if the force is constant. If the force is changing, then you have to do the integral of force times distance, which many of you can. I mean, so many of you are in calculus, but we're assuming that most of you are not. So we can only calculate the work if the force is uniform, and the force will only be uniform if you are in a constant field. So if you are in between the plates of a parallel plate capacitor, the electric field there is uniform. So if we have a charge here and we push it from one plate to the other plate, we can calculate the work that's done by using the equation delta V equals work over charge. Okay, so I'm glad to see that Josh was exhilarated by that. Josh, just wait until next year when you take U of U physics, because then you'll be doing this same thing, but for non-uniform charges, and you'll get to use all your calculus skills. So Kiker, are you disappointed? The way you worded your question there makes it sound like you're disappointed. You're saying, what, is it that easy? I was expecting something hard. Okay, so let's see. So somebody here had a question. So Yazin had a question, how do you do the derivation online if it's a test? Okay, yeah, I'm going to do next test a little bit different than I did the last test. Canvas can handle multiple choice questions really well. Canvas does not handle the free response questions quite so well. So I'm going to do it differently. Next time we have a test, I'm going to have most of the test is going to be multiple choice. And then I'm going to do a couple extra questions where you're going to have to write your questions on a piece of paper and photograph the paper, and you're going to have to upload a photograph of the paper. Or if you want, you could, do them on a computer using computer graphics software or something and upload that. But that's what I'm going to have to do. Okay, so Victoria is asking me to go back to the derivation. I can do that. Can you tell me why you want to go back there? Well, or did I just go too fast? Was that the problem? I just went so fast you couldn't write it down? Okay, yeah, that was the problem. I just went too fast. Okay, so I'll pause here for a little while. So Jaren, I see you turned on your video there. Is that because you have a question?
That was by accident.
Oh, okay, all right. Okay, so I think, excuse me, whoa.
Bless you.
Don't worry, sneezing is not a common symptom of coronavirus. Yeah, sneezing is just a sneeze. Okay, so I trust everybody's got that written down, so I'm going to go on to the next ones now. Okay, so in your homework tonight, they're going to give you problems like this. So they're going to say that we've got some known charged particle, like for instance, an electron. Our electron is going to be your author's favorite particle to go pushing around from one place to another. So he's going to say, let's suppose we've got an electron and we put it inside this field here. So right here where I'm pointing, let's say we have an electron right there. Okay, so let me ask you, oh, this disappeared. So let me ask you guys, if I were to put an electron right here, it would feel a force acting on it. What direction would the force be? Would the force be an upward force or would it be a downward force? What do you guys think? If I put an electron in between here, so Jaren is saying that it's going to be upward, and it looks like other people are agreeing. But Jaren, a question for you, the electric field vector is pushing downward. So now I'm not saying you're wrong. I'm just saying I want you to explain your reasoning. Because most people, they would look at it and they say, well, the electric field vector is downward, therefore the force should be downward. But you somehow think otherwise. Okay.
See, it's not necessarily that the force is downward. This is what I noticed. The top plate is positive, the bottom plate is negative. Electrons are negative, so one, the bottom plate is pushing the electron away from it, and two, the positive plate is pulling the electron towards it.
Okay, excellent. You are 100% correct. That is an excellent way to think about it. And the other way to think about it is this. These arrows that you see here, those are the electric field arrows. And remember, electric field is always defined in terms of positive charges. So the arrow for the electric field tells you what direction a positive charge would go. But an electron is not positively charged. An electron is negatively charged. So that means the electron is going to go in the opposite direction of what the electric field is pointing. So make sure that you guys think about it both ways there. Okay, so if I have an electron in here and I push it from one side of the plate to the other, okay, because the field is uniform, I can safely assume that the force will be constant. And so then I can easily calculate the force. And if I know what the distance is, then I can calculate how much work we're doing. Okay, so those are the kinds of things you're going to see in your homework tonight. All right. Now, okay, so you see here the arrow, I'm flipping the arrow back and forth. Okay, so sometimes in your homework tonight, they're going to say, all right, we're pushing a charge from A to B. So how much work are we doing? Other times they're going to say, no, we're not pushing from A to B, we're pushing it from B to A. So just be really careful with your plus and minus signs, and be careful, to read the problem carefully, and you guys should be good on that. Okay, so what if we're not inside the plates of a parallel plate capacitor? What if we are out in some place here where, like, for instance, if we're near a positively charged sphere, when we push the charged object from A to B, do you see the problem? The problem is that these arrows over here, they're really close together, and over here, the arrows are further apart. What that means is the electric field is changing. So if I want to calculate the work done going from A to B, I'm not going to be able to do it the same way. I'm not going to be able to say that it's just whatever the E vector is times the distance, because the E vector is no longer constant. So you're not going to see problems in your homework tonight like this because you have to use calculus in order to solve it. All of the problems that you're going to see in your homework tonight are going to be like this, where you have a parallel plate capacitor. Okay, and boy, even the calculus, even the U of U calculus and U of U physics students wouldn't be able to do one here. Here, the electric field is really completely strange. If you go from A to B here, trying to figure out how much work you did in this situation would be so complicated. Even the U of U physics students wouldn't be able to do it, at least not the ones who are taking the first year U of U physics class. You'd have to be like a senior. This is like a senior level university problem to solve this. Could I do it? Yeah, I could, but it would not be easy. It would take me a lot of time, and no, I'm not going to do it right now. Okay, all right, so this here is a capacitor. So what you're seeing here, these two plates, I called that a capacitor. And some of you, not even for cash. That's right, Kiker, not even for cash. Not right now, anyway. Okay, so let's get back here. So this thing here, where we have these two plates like this, I'm calling it a capacitor. And I'm hoping that you guys are going to say, wait a minute, capacitor, where have I heard that word before? And then you're going to say, oh yeah, this is where I heard it. Back when Mr. Hendricks was talking about how computer memory works, and we had this thing here that we called the gate. And if we put positive charge on the gate, then the charge can flow through here. And this place where we stored the charge here, Mr. Hendricks called that a capacitor. And yes, that is exactly the same. So a capacitor is a device that stores charge. And this device right here is a wonderful way to store charge. Think about it this way. If the bottom plate was not here, okay, so let's pretend that all I had was the upper plate. The bottom plate wasn't there, and I'm trying to store charge on this plate. So I need to take plus charges, and I need to push them into the plate. Now, if the bottom plate isn't there, let's see, I wonder if I can, let me get a little shape here. I got too much stuff in my window here. Okay, hang on a sec here. I'm almost done. Okay, what I'm going to do is I'm going to fill that with white. Okay, and let's even get rid of the line while we're at it here. Okay, so I'm going to put this right there. Okay. All right. So, and I didn't hide it all. Let me hide it all. Okay, so if all I had was the upper plate, okay, and I want to push charges onto that upper plate there, it's going to be hard. those charges they're already pretty crowded. Now, if I want to go put some additional charges on top of there, they are going to fight me, all right? But if, in addition to that upper plate there, I also have the lower plate, okay, then all these charges, all these plus charges that are crowded together, they feel a little bit more relaxed. The presence of all these negative charges down there, that helps relieve the electrical pressure. Or so if I want to push a positive charge onto this upper plate here, the fact that there's a negative plate underneath there makes it a lot easier for me to do that. And that means I can store more charge in the capacitor, thanks to the fact that I've got a -1 down here. And in fact, the closer I bring these plates, the more it helps me, because all those plus charges up there that hate each other and they want to get away from each other, if I bring that negative plate even closer and closer and closer, that helps soothe them. And so that makes it easier for me to put more charge on there. So the closer I bring those plates here, the easier it is for me to store more charge on there. And so having a positive plate and a negative plate is a very important part of a capacitor. It allows you to store a lot more stuff in there. Okay, so let me move on to here now. Okay. All right, so what you see here, this is pretty typical of what your homework is going to be tonight. We've got a parallel plate capacitor, because that makes the math way easier. And in fact, for most of you, it makes the math doable, all right? And so what they're saying is here that we've got a parallel plate capacitor, and we know, oops, hang on a sec. I'm playing with a couple windows that I can see on my screen that you guys can't see on yours. Okay. All right. Okay, hang on a second. Okay, so we got this parallel plate capacitor, and we're pushing a charge from one plate to the other plate. So how much work do we do? And I think the book does an excellent job of describing how to do it. So I don't think that I really need to spend any time doing this. Let me just recommend that you make sure you work through this example problem. And if you do that, then you shouldn't have too much problem with the homework. Now, there is one thing that the book talks about here that's extremely important, and I want to make sure that you guys know how to do this. Okay, so this is something called the Millikan oil drop experiment. Now, when you took chemistry, did Mr. Miller talk about a guy named Millikan and how he determined what the charge on an electron was? Okay, so Josh is saying yes. Okay, good. All right, Jaron is saying sort of. Okay, well, we're going to do better than just sort of this time. We're actually going to do the math here in your homework tonight. So what Robert Millikan did here was he took a perfume spray bottle, and this is the old-fashioned perfume bottles. You don't see these anymore, except maybe in an antique store. But if you take a bunch of perfume here and you squeeze this up here is a little rubber bulb. So you squeeze it, and it forces air through there, and it sucks up a little bit of the perfume. And so what you get here are a bunch of very, very tiny droplets. But he's doing one thing that the perfume manufacturers don't do. He is doing something that's not shown in the picture here, that puts excess negative charge on here. So each one of these little oil droplets has a bunch of extra electrons on it. All right. Okay, so now these oil droplets, they want to come down here due to gravity. And so they do. And they hit this upper plate here. Now, it's not clear from the picture here, but can you see right where I've got the arrow here? There's actually a little hole, a tiny little hole in the plate. So most of these oil droplets, they hit the plate and they stop, but a few of them, they make it through the hole. And so then what happens down here is you get an oil droplet that has an excess of negative charges on it. And so it's exactly like that problem from the homework that we did, where I've got a little ball here. Gravity is trying to pull it down, but what Millikan did was he took a battery and he connected up the battery so that the plate on the bottom here is has one charge, and on the other has an opposite charge. And so the oil drop is going to feel an upward force because of the electricity that's equal and opposite to the downward force due to gravity. And then he had a little microscope. You can see over here at least a portion of the microscope. And so he's able to look and he's able to see the size of the oil drop. And so what he can do then is he looks at the oil drops and he sees that they're falling, and then he adjusts the voltage on the battery. You can increase, and if you're clever. I don't want to know the details of how it works, but it's possible to have an adjustable battery, basically. So you can increase the voltage or decrease the voltage on the battery. And so what he would do is he would increase or decrease the voltage until he would get the oil drop to where the downward force of gravity was balanced by the upward force of the electrical charge. And then from that, from looking at the size of the drop, he could figure out what the mass of the oil was. And then from that, he could figure out what the electrical charge was. And from this, he was able to figure out what the charge on an electron is. Because what he found was that the electrical charges did not have an infinite number of ranges. They came in steps. Okay, there was a step size. You could either have 1 electron or 2 electrons or 3 electrons, but you couldn't have 1.5 electrons, or you couldn't have 1.3 electrons. There was an integer number of steps there. And then he looked at what the step size was, and from that he figured out that that was the charge on an electron. Okay, so go ahead and read the book. I think the book does an excellent job of doing it. And don't be surprised if you see a test question next time we take a test. I might ask a question about the Millikan oil drop experiment, wink, wink, nudge, nudge. So make sure that you study that and understand that. Okay, so we're pretty much done with the lecture here. Here's the homework. So first thing, take the daily quiz. So this is my way of taking roll, basically. I mean, right now, in fact, let me see. There are only 40 people participating right now. But that's both of my A-Day classes plus my B-Day class together. There should be a lot more than 40 people online right now. So in order to give you credit for attending, what I do is I do the daily quiz. And my intention is that most of the time the daily quiz will be very similar. It's very simple. So like, for instance, what color is my shirt? Or remember last time it was the secret word? Did that work out okay for you? Did you guys like that secret word question? You want to do that again? Let's see, what should the secret word for today be? Somebody want to suggest a secret word? Candy, satchel, Corona. Oh, Corona, I like Corona. Do lasagna again? Okay, so tell you what, candy was the first one I saw, and Corona was another good one. Okay, so these are the 2 secret words that we're going to do for today. So you never know. Correctly identifying the secret words might possibly be a question on today's quiz. You never know. Okay, so don't sweat the quiz questions. They are intended to be pretty simple and easy. They won't always be like secret word questions. I will sometimes put an actual physics question on the quiz, but it won't be hard. Okay, so that's one thing that everybody needs to do in order to get credit for attending class. And then the other thing is the homework. So today I want you to do problems 16 through 19 from chapter 21. And also don't forget about the extra credit assignment. That's something that I think is really important that you guys need to know, and it's not in the book. Okay. And yes, Annie is saying that yes, the extra credit problem was due on the 3rd, and that is correct. Oops, so that is what it's, whoops, hang on, let me go back up. Midnight on Friday. Thank you for correcting me on that, Annie. I'm willing to call that a wig point, even though that's not a physics error. I'm willing to call it a wig point because class is pretty much over, so I'm not worried about wearing the wig. Okay. Any questions? Any questions before we end the class? Wear it anyway? Okay, tell you what, Kiker, just for you. I wouldn't do this for anybody else, but I'll do it for you if I can find it. Okay, there we go. Okay, there we go. Yay. Okay, so can we change the wig points to 2? No, we got to stick at 3. But all right, so if nobody has any questions, then I will go ahead and stop the recording and end the class. So still not seeing any. Oh, okay, there's a question. Why does the Q have an apostrophe in it? Not really sure which thing you're referring to there, Joey. Sometimes what they do is if they have two Qs, one of them, they put an apostrophe on it just to let you know that it's different than the other one. So yes, it is a prime. But yeah, don't worry about it. Just you got one charge, the other charge. You can call them Q1, Q2. You can call them QA, QB. You can call them Q and Q prime. I don't care what you call them. It's just a way of designating it. Okay, you dig the wig, huh? Okay, good. All right. Okay, well, with that, I think I'm going to go ahead and end the recording.